Okay, welcome back. Next we have Ken and Reza talking about time series data, processing time series data in Apache Beam. Really excited about this talk because I think it's a problem that many users face, and they don't know, they have their own solution to the problem, but I think Reza and Ken will provide some systematic building blocks to solve this problem. And yeah, have fun. Thank you.
All right. I'm up first. I'm going to sort of talk about, I'm going to blaze through the very base. Everybody here has seen many intros or builds Beam. So I'm going to just start with some context setting and talk about how Apache Beam applies to these massive out-of-order streams. And since everybody already knows the primitives of Beam, I'm going to take the opportunity to philosophize about why they are the way they are a little bit. And then talk about stateful processing in Beam. And this will take only about half the time, whereas it'll take the other half telling you about how to use them to accomplish the time series uses. So, starting with massive out-of-order streams, right? Streaming drives Beam's design, and I want to highlight aspects of that. You can't process all the data because you don't have it. When you run out of data, you aren't done. You have to wait. And you kind of have to guess when you have all the data, right? These are aspects of something being streaming. And massive, that's more like it. That's more massive. Much more data. And you're going to need a lot of machines, and you're going to need it to be embarrassingly parallel. Right? We're only talking about embarrassingly parallel computation when we talk about Beam. And out of order has to do with the fact that these are messy sources. Blender is literally messy. The internet, you assume, is messy, but nobody knows how it works. And yeah, this is Beam, right? So all of these factors mean you can't just kind of do basic imperative programming, procedural programming that we all know and love. These ideas that come from functional programming yield all the parallelism and embarrassingly parallel capabilities of Beam, right? Like associative and commutative aggregation is what allows you process out of order stuff correctly and to do divide and conquer and work stealing. So I'm just going to highlight the design of Beam with respect to the different ways, simpler ways that you can do data processing before we get to more complex ways. So this is a pipeline. You saw it in Andrew's slide, which was originally my slide anyhow. I'll talk about some of the different pieces that will be in one of these graphs. You know Pardue? Raise your hand if you know Pardue. So it's like, yeah, we all know Pardue. And this diagram shows you how very simple it can be. Every item is processed independently, right? That's what it enables massive scale. And because there's no dependencies between anything, that also makes it support out-of-order data. And it doesn't matter if the data is infinite, you can still take one element and process it. So it hits all the points. The next thing we've got is group by key or combine per key. And let's see. We have to group all the elements with a common key. Here I'm using color for the key. It often has a stateful implementation, right, in streaming. If you're from the Flink world, they call this stateful processing. I don't call it stateful processing, but terminology is not the point. The point is that it's really about applying an associative and commutative combiner. And that could be appending, which is the basic group by key, or it could be something that you've written. Associativity allows divide and conquer, hotkey, fan out, combining before you shuffle this data, and commutativity allows the out-of-order processing. And so in Beam, you're always combining per window, right? You have an event time window, and eventually the event time window is going to end, and this is what makes combine work on a stream, because otherwise you don't actually know when this thing is ready. And per window combine also sort of, if you do have a stateful implementation, it allows you to manage your state automatically. So those are sort of how the aspects of massive out-of-order streams influence the design of combine. And it just works, right? It's great. You can parsing incoming events and filtering out bad data. The really easy cases are easy. Put events in 10-minute windows, slide them every 2 minutes. Let's see. There's also sessions, which I'm not really going to talk about here. But you can sum per hour, output when you have the whole hour. This is like super easy. most of your pipeline probably still uses these. But there's lots, I think at this conference I've had at least 5 people say, well, that's all well and good, but every single person is going to use state and timers. I was like, okay, well, maybe. So it happens when you're doing this that the Beam's primitives don't really give you the expressivity you want, right? This is my favorite one. I'm getting not trying to do this with windows and triggers, right? Like, you just may not know how to express it in a reasonable way, or there may not be a reasonable way to express your logic. Your aggregation might not quite be associative and commutative, or it might be associative and commutative in a way that needs careful handling, up to some equivalence in your output. Or, you need to output when data is not coming in. That's something that you simply can't do with the other primitives. So that's where stateful processing comes in. Was that?
Oh, sorry, it was just a bit like it was falling behind, that's all.
Oh, was it falling? Okay. Oh, they just look the same. They just have different words at the bottom. Oh, sorry. Yeah. But yes, okay, that was fast. That's great. I want to leave as much time as possible for time series. So stateful processing. This is how I draw it. So you've got Pardue is element-wise. Combine reduce fun is grouping by key. And state and timers, I'm going to walk over here so I can point at it a little bit. Yeah, it's a new primitive, right? It's not a variation on an existing primitive, really. It's group the stuff by key and then do element-wise. And this enables sort of lower-level implementation, right? You can say it can look like a for loop. Like for each element, I'm doing this and I'm updating my state. Let's see. The things to note are that the way it works with massive out-of-order streams, you still have this partitioning by key, and that's what makes it work with massive stuff. And then the out-of-order and the streaming, in this case, they're sort of on you. And then we'll get into a little bit of that. So, I want to call out that since this is a more expressive primitive, it's lower level, it has a bunch of knobs, and what that means, and we don't perhaps emphasize so much, is that there are fewer ways to implement it. This is what lower level actually means, right? It doesn't mean it's closer to the metal, because it's actually not. It just means there's less sort of optimization wiggle room for the runner, but you can express a lot more different computations this way. So, this is what it looks like in Java to have a state cell that you update, and it's charted per key and per window. So, you have to write your do fun for Pardue. It has to be keyed, and then you declare the state cell that you're going to use, sort of as a type here. That's what it is now. And here you say, okay, state specs, it's a value state. We're considering renaming this read, modify, write state. This is just a cell. You can read it, you can write it. And it can infer the coder most of the time here. Otherwise, you might have to provide a coder. But I hope you won't have to. And then in your process element method, in your sort of list of automatically sorted out parameters, you say, I want to use this state cell, so give me a handle to it. That's this value state. And it looks like, counter.read, counter.write. So it's just a state cell. Okay. And the design of this is made so that it can all be validated before your job starts running. So that's part of this. Like, we're going to check that the counter state exists. We're going to check that the types are right. I'm going to check that the do fun has a key. And then this is what timers look like. They, again, has to be a key do fun. And you declare the timer in a similar way. Let's say I'm going to start buffering a bunch of data, and if I don't get a magic event I'm waiting for soon enough, after a little bit of time passes, I'm going to flush all my data, produce some output. So a timer spec is the description of what kind of timer I want. And in this case, it's a timer based on how long the computation is going, and that's why it's a processing time timer. And it looks just the same when you use it. You declare that you want to use it in your element method. So element comes in, and then maybe I buffer up the element, and I set, this flush timer, I'm going to set it for like now plus 5 minutes. And finally, you have to have a callback. And let's see, I used the wrong ID. This will cause a failure before the job starts to run. So I'm going to go back, I'm going to edit this. It's going to be flush dash timer. And this is what's going to get called when 5 minutes have passed. And here, this parameter list for the onTimer method has all the same sort of magic parameters that you can put in the process element method. So you can access state, you can output, and I think you read side inputs. We have. Okay. So yeah, it looks like an imperative callback. We've got things that look like mutable reference cells. We've got things that look like imperative callbacks. So it's kind of also like a simple programming model. I'm just going to walk through, like, this is sort of how an example works. We have some reference transforms in the SDK that look like this. So in this situation, I'm trying to write a transform. And I'm just trying to take every element that comes in. I'm going to hit some auxiliary service to get some metadata about that element, and then I'm going to output the result, right? And it's very easy using Beam to get blacklisted from whatever service you're trying to hit if you don't own it, right? So, and it's also super inefficient to just do this naively. So what I'm going to do is I'm going to try to buffer stuff up and do it in little batches. So first thing, all these elements are coming in. This is my process element method. I apparently called it on element in this picture. This is process element. And the first thing I do when I see some data is like, okay, let's just call me back in half a second. I know that I'm just going to see what I can gather within the half second. And then every element that comes in, maybe I'm transforming it a little bit to store all the data I'm going to need to make the request later. So little red cylinder over there. I love writing to magnetic drums. Let's see. In half a second, the runner's job is to call, how's my on-timer method to be called, right? So this timer comes in, and because I can read all my state, maybe for like request metadata, or so the metadata for requests has been buffered, and I'm going to read it out. I'm going to make one batch request. It's exactly what you want. It's wonderful, and then I output, I output the return value batch.RBC, and maybe I break it apart again, so that anyway, outside this blue box, all I say is events coming in, events coming out, and they're enriched, and they didn't pay too much for this cloud service, and they didn't get blacklisted. Okay, so yeah, that's the user viewer transform, right? I think like one of the tenets here, right? Like, could I have made it so that this was like a nonsensical output result that was non-deterministic? Very easily, right? So there's a little bit of care. You're not working with a primitive that is going to prevent you from doing crazy things. You can do crazy things, but it's also, the point is that if you package this up into a reusable P transform, it needs to work with all the rest of the Beam model. So it needs to interact with windowing in particular. So somebody's going to window in hours and then call your function, right? And is that going to work the way they expect? And in particular, they would expect it to respect whatever windowing they choose. They still get enriched events, and they don't care about the fact that you're using this mechanism. So what does it take to make this just work? Well, the basics are that state is per key and per window. I think a lot of people discuss keyed state. I think that term was coined a while ago, and it's been used in a few places. This is always per key and window, because what the window gives you is this deadline after which, plus your allowed lateness, you can eventually drop all the rest of the incoming data, which means none of the state is reachable, and you can throw it away. So here I've got more of like a rainbow sherbet magnetic drum, and so the red stripe is per key. Each color is still a key, right? But in the red pen stripe, I'm aggregating my own activity per hour here, and so I have a separate piece of state for each hour, right? From 9 to 10 a.m., I do try to set aside a little bit of time for the code right now. And I added you to this slide just now. Reza was on a flight between 8 and 9, though. Yeah, so here I say bonus down here. That's not true. This is completely central. These slides are a little bit out of date in terms of how I think about state. Right. So as the watermark and the windowing advances, once the watermark says, all right, we're at 10:15 a.m., I can throw away that row. And so as long as you have sort of sensible windowing set up, the advancement of the watermark is going to make sure that you don't have to manage your state or clear it out or anything. And another aspect, which is a reason that you need to take care and make sure that your transform respects the Beam model, is because it's always the intent that you can achieve the same results on an incoming stream of data or on an archive of that stream. Right? And this takes a lot of forms. It doesn't just come out of a faucet and get written on paper. You can use Kafka and PubSub and files and BigQuery, and they all have different ordering behaviors, and how they change the order in sharding. And here, I do say equivalent results. When I write about this, there are use cases where, for example, like I want to stick a unique integer on every element. I think that's like it's useless, but it's like the simplest way to explain that that's fine. Like you don't have to get the same results. You just need the output to sort of have whatever property you're looking for it to have. Okay. So just the types of state that exist. I'm going to just talk through these in a little bit of detail in terms of like how they might apply to the use case. So value state I demonstrated. This is just you can read and write a value. It's always the whole value, so that's sort of the downside of it. But it's very flexible. The next kind of state that's pretty common for like a buffering use case is a bag state, and a super cheap append. You can send just one element over the wire, and it's the runner's job to accumulate it into a bag, which you can then read back in sort of a paged or streamed manner. There's no ordering on the read, and that sort of helps you remember that this stuff was out of order to begin with, and you shouldn't be assuming anything about the order. If you want order, use a list state and be careful. Use a list and a value state and be careful. Combining state is essentially it's like a bag of accumulators, or it's rather you don't really know what's going on. You give the runner a combine fun, and it can use that to compact the state. So a bag state can get really big. A combining state is sort of expected to not ever grow, or at least have sort of bounded growth and is managed by the runner. Set state should have cheap membership checking, right? You don't have to read the whole thing and then check membership. You can just do it with a quick query. And map state is very similar to set state, except for you have a value associated with the key. And as map state and set state both have cheap partial rates, just like bag and combining states. Timers, there's just two types of timers. Processing time and event time timers. And to be honest, these are just completely different uses. So processing time timers are most useful when you want to ensure some property of your output, like you have a continuously updating dashboard. That's like the most obvious thing. Is you don't want the data to sit around for too long, right? Or in the buffered request, you don't want to buffer up unlimited requests. You want to have some sane limit. So you might also, in that case, have a limit on the number. You probably keep a counting state as well. You can only set it for relative time. I think you can still only set it for relative times, right? Because that's all it really makes sense. Like if you're processing and you say, I want a timer for like a particular date, that kind of makes your pipeline extremely weird and inflexible. But it's most useful for doing something a certain fixed distance in the future. And event time timers have more to do with the life cycle of your data. So in particular, right, there's moments where you say, okay, if I'm doing hour windows, I might do something when the window is half done, right? I think I'm halfway through the window, and then I have a callback, and I do something then. And there's a very special moment, which is when the window is complete, where you really ought to do something because don't leave data buffered in state, right? So it's super important to always sort of set an event. If you're using state and timers, remember that you need to set an event time timer for the end of the window or for when the window plus allowed lateness and it's about to expire so that you clear out your state. I think this is just reiterating what I said before in case you're like, man, this is the ultimate primitive. It is not the ultimate primitive. It is extremely flexible, and you should definitely feel free to use it and get the job done. But don't start thinking in terms of reducing the whole world to this, or you'll start thinking in terms of execution instead of your logic. And yeah, I have a list on my thing, the things you can't do with this. If your state is kind of like a combine, it will not receive combiner lifting. You cannot do hotkey fan out. And yeah, that's all I want to say about that. All right, what else can you do with state and timers? These are some use cases that we've sort of thought through and been like, well, we probably can't do this. We need state and timers to do these things, right? Domain-specific triggering, like the Beam triggers aren't what you need. Slowly changing dimensions and sort of managing the fact that like an exchange rate changed. Most stream join algorithms require like sort of some tweaky state management, and we're still building up all the capabilities to do algorithms like join matrix and join by click, which keep buffers of stuff that's coming in from each side of the join and timers of different sorts to garbage collect the stuff that's old from those buffers. I'm going to skip these last two. I don't think they're as interesting as getting on the time series.
Good. Cool. Thanks, Ken. So what we're going to explore is a concrete use case where I've been trying to solve this problem with time series for a while, and state and timers are beginning to give me the primitives that I need to actually solve it. Some of this stuff is still slightly experimental, but with that caveat, so solving for time series. What is time series? So this is Wikipedia. Essentially, time series is points of data that are sequenced by time. Doesn't seem particularly problematic, but then we're doing distributed processing, and there's a few things in here that make you go. First being the words order and sequence, not fun things in general. Everything's distributed. The other part is this piece, and we'll cover this in a little bit more detail now. That is, you tend to, when you're working with time series, you tend to work with time intervals, so between 0 and 1 second, and 1 second to 2 seconds, which is great, and Beam is awesome at processing large amounts of data, but what does it do when no data comes in? It doesn't do anything. And quite often with time series, just because there's an absence of data doesn't mean we don't want a data point in there. Now, it could just be as number 0. For example, if you imagine IoT time series, this sensor didn't give a reading. In time series for financial services, it could be that there was no tick in the stock market. So no one had to ask or a bid for a specific instrument at that point. Doesn't mean there was no value in that instrument. It just means the value is probably the one that is last seen. So the last time you saw a tick. So what does that look like? In this table, so the x-axis is 5 time series 1 to time series 5. And the y-axis is time intervals, so t0 to t1, t1 to t2. So imagine this could be, second gaps, it could be minute gaps, it could be day gaps. In the table, every time there is a data point for that time series in that time interval, we get one of those, I think it's blue, but over here showing grey in my house, grey dots. And when there is no data, we are getting those squares. So how do we actually fill these things up so that we've got something that looks like this? So, and I shouldn't use these different colours, I should use different shapes. Sorry for folks who have issues with colours. But essentially what I filled it up with is these generated data points where we're creating a heartbeat or an impulse or something that allows the system to be able to do some processing when there was no data. Now, there are a few ways that we can actually solve for this problem. I'll go through some ways, first of all, that can be done that don't use timers or state, but have some difficulties and ickiness being a technical term. The 3 options. The first one is we create a heartbeat or an impulse in a system outside of your Beam pipeline, and that generates a piece of data that we can then work with. The next one is we somehow generate this impulse or heartbeat within the pipeline itself. And the final one, we're going to use some of Ken's nice timer API stuff to actually create what we call a looping timer. So the first one, on your right-hand side, you will see our time series sources. So this is the real data. On the left is an external system that's creating an impulse at the same rate as the interval window period. So if it was 1 second, it would be firing something every second. If it was an hour, it would be firing something every hour. Now, problem 1 with this is we've created for every pipeline, we have to have something outside our pipeline, a system, some piece of code. And it's pretty trivial code, but it's still code that has to run somewhere. Then we have to watch it. We need to make sure it doesn't fall over. If it does fall over, then we've got to So not so fun. There are some other issues with that as well. So if we're creating 1 impulse, so 1 tick, right now we've got 5 time series. Now the time series will get expressed within the Beam pipeline as group by keys. So start imagining each time series is a different key. So now I've got 5 keys, I've got 1 impulse. I now have to do a fan out. And that fan outs are, we need to think carefully about them whenever we do them, because you're generating this one thing that then suddenly needs to send stuff to all other keys. We've only got 5 keys here, but Financial instruments, there could be thousands or tens of thousands. IoT could be hundreds of thousands or even millions of these keys. And that fan-out starts becoming more and more troublesome. The other part, which is tricky when you start working with real data, is dynamic key lists. So you've got IoT devices, you got 100,000 this morning, by 2 o'clock you might have 99,000, by 3 o'clock you might have 110,000, so the list of keys is constantly mutating. So now we need somehow, before the fan-out, to tell the fan-out the list of keys that it should work with. Again, you could do this with an API call and stuff, but this is bringing some nice technical debt and it's getting very icky. You could get clever and use the pipeline itself to tell you the list of keys. So one way you could do that is the time series source. You could do a distinct on the key. That gives you the dynamic list per time interval to pass into the function. But again, imagine there's 100,000 keys and we're doing 1 second intervals. At this point, we're having to do a distinct on all of those and get that data to the worker or whatever that's doing this fan-out. So again, it's bringing a lot of technical debt and not particularly efficient. So one way we could solve this is option 2, get rid of some of the ickiness, and that is instead of having an external system that sends this impulse, we can use something called the generated sequence transform, which is available in Java and I think Python as well. And what that does is it creates a source that will just ping at a rate that you want. So we got rid of one bit of ickiness. We now no longer have this external system to worry about. But all the other stuff is still all there. Here, we can actually now think of getting rid of that by using timers, and specifically event time timers, not processing time timers. We want this all to be within the context of the data time, not the wall clock time. I won't go through this because Ken has already done a wonderful job covering that. I have a slow brain, so I like to simplify things. For me, in my head, a timer is just an alarm. So I'm setting alarm and I'm going to do something when that alarm happens. How does this help us? So let's imagine that we have 4 time intervals starting from 2 o'clock every second. So each one of these blocks is going to be one of our time intervals. As we go through, we've got 4 seconds worth there. Sorry, 3 things. The data points that come in are going to be in circles, so we have a data point here. What we can now do is, at the time that I get my first data point in this interval, or any of the data points in that interval, I can set a timer. And I'm going to set the timer to go off in the next time interval. For those who've used timer, you'll know that there's a little bit of ickiness I need to cover, which I'll cover in the next bit. But let's imagine right now I can set a timer into that next time interval. Okay, what does that mean? Well, in the next time interval, I have no data. Nothing's happened. However, I do have an alarm. So my on-timer fires in that next time interval. And now, with that alarm, I can do things, like for example, I can insert a 0, because there was no data, or I can be very smart and call other systems and do other things. And I can also reset the timer. So now, we have this perpetual timer that will always fire in every time interval, and it is doing this per key instead of as a single impulse that we're having to fan out. Because every key that comes in, if this was time series 1, the same thing's going to happen as time series 2, time series 3. So now per key, we're having this alarm clock that can keep continuously firing across the loops. Now, the reason this is a little bit icky is you can't actually set a timer to go off in another interval window. So if you're doing fixed windows and you want to set the timer, it will go to the max, and as Ken described, at the end of the window, everything gets garbage collected and goes away. So you can't set the timer. So how do we do this? We use a trick, which is we will use the global window. So a global window, everything in a beam when you first start, if you don't do any windowing, everything's in the global window. Essentially max is set to infinity. So we will process our timers within a global window by dropping the keys that are coming in into that global window. This allows us to set a timer at any point in the future. And what we do is we set the timer, we have to pass in a parameter that says our time intervals are 1 second. So then we set the timer 1 second in the future. So that trick allows us to make use of the timers for the loop. It brings in another area that we then need to think about as well, is this is going to go on forever, right? So we mentioned the list of keys may change, right? The list of devices in that first one, they might go from 100,000 to 90,000 IoT devices disappear. What we don't want is a system that will forever continue growing in the keys and the timers that are firing, because nothing's going to stop this. So what we need to do is think about something like a time to live. And a very simple one would be if a key has had no real data, and you can check that because you can check every time the timer fires whether real data is coming or not. If it's had no real data for 5 minutes or 10 minutes or whatever the business decides, you stop setting the timer. So now you have timers that can fire all the time with a key, and they've got a way to stop at some point. So the advantage is there's no fan-out operation, everything's done per key. The timer itself will initiate when you first see a value. The time to live, there's never going to be a perfect way to do the TTL. You could do something like call out to another system, but whatever you do, it's a slight compromise that we have to deal with. The other thing that we need to then deal with, so problem one, we now have the ability to fire in every single time tool. The next problem that we have with time series in general, which again we can solve now that we've got this looping timer, is what data to actually put into those gaps when we fire them. So here we have our table now with data points and generated data. But we haven't covered what actual data we want to use there. One of the common things that people ask to do is hold and propagate. So in the financial services use case, if the last value seen for a stock was $1, now that there's no value seen, we still assume $1. So we need to somehow carry that $1 over to the next point when the on-timer fires. And to illustrate this, I'm going to use a concrete use case, and that is to build candlestick graphs using the data that's coming into Beam. And candlestick graphs are wonderful. If I remember correctly, they were invented by a Japanese rice trader in the 1800s, I think. And they're super awesome because in this one graph, you serialize lots of pieces of data. So you have the opening price seen within the time interval, you have the close price, you have the lowest price, you have the highest price, all very effectively shown in this graph. Okay, so let's try and build this using our data points. And the data points are, in this graph we've got two stocks, stock A and stock B, various prices that we're seeing, and the time when we're seeing those prices as we move forward. So obviously there's gaps. Those gaps means there was no activity on the market for those pieces. Now, what I'm going to do to this in Beam is if we had this data and we run a fixed window of, I think I do it over a second, and do a group by key. So what you'll end up with is these fixed time intervals, from 0 to just before 1 second, 1 second just before 2 seconds. You're going to end up with an iterable of all the values you saw within those time intervals. So that's very standard using the primitives. As Ken was saying, you don't always use state and timers. This is just standard fixed window group by key. At this point, we've got this set of data. We've got gaps in stock A for the second time interval, and stock B has got a gap here where there's been no data. And we know that we can fill that data with the looping timer. So what are we going to try and use for these data points? So in a normal candle where there has data been seen, you'll have an open and closed position. The open position is the first value seen in the window. The closed position is the last value. In this second window, we also have data. So again, open and close is pretty straightforward. Now, a lot of banks and institutions will say, and this is sort of depending on what they're trying to do, you could use the open as the first value seen in the window. But some would say that actually the correct thing to do is have the closing value from the last window be the opening position in the current window. And that is more accurate and makes sense, right? The last time I saw a value was in the last window, so if something comes in the middle here, the actual open position should be what we had before. Okay, so now next, we don't have any data. What are we going to use? We know with looping timers we can generate an on-timer event. what do we actually do in that on-time event? How do we get an open and close when we have no data? Well, we can take the close from the previous one and bring it into the open. And this step is where we're going to start using state. Yes?
I'm getting nitpicky on the actual candlestick, so tell me if this is too much of a distraction otherwise, but it seems like this implies that the close is consistently lower than the open, or how, like if time is going left to right.
So this is just, I've just put the, for the display, the open and the close.
Yeah.
It could be that they change and they change color when that happens.
Okay.
If I remember, if it's the other way around, if the min is less than the other,
Okay.
the color changes.
All right, cool, that makes sense.
Yeah, thank you.
Yeah.
So we take the close of the previous one into the open, and because we've never seen any data, we can assume that the open is also the close, because there's been no data at this point. So for this piece, we're going to use state to solve the problem. And Ken has described state for us, so we know we can store a value in state and we can retrieve it. With event time timers, we're actually firing the event time timer in the next time interval, so we can actually pull the data out. But a bit of ickiness. So as Ken was describing, at the end of a fixed window, everything gets garbage collected. So I'll take all of this care to put the state into the value in state. When I want to actually use it, which is the next time interval, it's already gone because the garbage collector's kicked in. How do we solve that problem? Well, we can go back to using global windows. And the flow for this is we create fixed windows, we do our computation, we actually calculate partially the candle, so we calculate as the min-max and all those values within the fixed window. Then we re-window it into global window. If you remember, the global window, max time is infinity. Great, we now have a way of having this data be available to us. But then we've got another bit of ickiness that we need to solve. The global window does not guarantee any order whatsoever. So in stream mode, it may just happen that things that you process are going to be processed in order. But that's entirely accidental. You should always assume it's all going to be unordered when it hits the global window. Okay, so how do we solve for this? We've got fixed windows, all pretty straightforward. What we need is we always need these things in sequence, so I take the right value forward to the next one. And the way we do that is combining both state and timers in an interesting way. So in this top graph, we've got these windows that are coming in, fixed windows, T0 to T3. So these have had some level of reduction already done on them on the data. I drop this into the bag state that Ken mentioned. Remember, bag state unordered. Okay, that's fine. So 0, 1, 2, 3, and we've got 1, 2, well, that should have 0 in there, never mind. But anyway, it's unordered. When the timer fires, every time the timer fires, we read everything in the bag state, we sort in memory, and then we output on event time with the state from the previous one moved to the forward one. So this allows us to actually move that value forward in the candlesticks. We're respecting the order of the processing. And in our data set, what this ends up with is, when we had no data before, we now can get the 1.53 out of here and bring it forward. So with that, we have able to solve both for lack of data and how to propagate those values forward. A few limitations. I mentioned sorting. It's in memory, so you have to be careful about the amount of data that you're pulling from the bag state to actually do the processing. There was talk on the dev list of a ordered map, which would make that all wonderfully easier. So who was working on that? Work faster. The accumulation. So if you remember, I'm using fixed windows going into that global window. You want to do as much reduction as possible before you get to the global window. That reduces the memory pressure. Today, some runners don't have map state. They only have bag state. In those instances, it's at the moment it's pretty inefficient. What we have to do is read the whole state every time, sort an output for every single firing of the event. There are ways around that, but that's not for this talk. And again, if all of the runners have map and order, that all becomes easy. The final bit that I completely deliberately ignored is late data, introduces a bunch of other things that we need to, ickiness, that we need to solve for. Yeah, so that helps us run with time series as a concrete example, and then and just summarize our stateful do fun.
Sure. I mean, I think you actually demonstrated a lot of this, right? You know, it unlocks new use cases like time series, having the stateful do fun. I think it was a great example of when you would get really tangled up doing it with, trying to figure out what kind of magic custom window I can write to do this. Right? I think we talked about that. And, didn't make sense. It was impossible. So it's portable across data processing engines, right? That's the main thing. But I want to emphasize, it's portable because it's abstract. And it works with event time windowing in that it synergizes in terms of automatically garbage collecting if you are not in the global window. And which word for present and historical data, which is sort of funny. That's all. That's the last slide. This is actually just the leave it up while we have questions slide.
Okay, great.